Welcome to Spring LIB.
Okay, in this problem we're asked to find the scattering angle for an incoming photon colliding with an electron via Compton scattering. We are given the wavelength of this incoming light, which is 0.1385 nanometers, and we're given the velocity of the electron after the scattering, which is 8.9 times 10 to the 6 meters per second. Because this velocity is considerably smaller than the speed of light, we do not need to use any relativistic corrections. It's reasonable to assume that the classical kinetic energy, for example, will suffice. The equations that we'll need to use the classic Compton scattering equation, which relates the change in wavelength of our light to a scattering angle, theta, which is actually what we're going to be solving for. We'll also need to know what the energy of light of this photon is. We can relate it to its wavelength by hc over lambda, where h is Planck's constant, c is the speed of light, and lambda is the wavelength of light. And we'll use, of course, the classical kinetic energy for this electron. For constants, we have Planck's constant in joule seconds. We have the speed of light, which is approximated by 3 times 10 to the 8 meters per second. And we're going to use the mass of an electron. Okay, let's jump into it. So starting up, we need to determine what the new wavelength is of this photon after the scattering. Once we know what this new wavelength is, we can figure out the angle. So in order to get this new wavelength, we can do conservation of energy. We can say that the total energy before the collision is hc over lambda. And the electron has no energy because we assume that it's at rest. So after the collision, we have the photon with a new wavelength and an electron with some kinetic energy. So we need to solve for lambda prime. We know v, we know m, we know lambda. So we need to solve for lambda prime. So doing some algebra, we can divide everything by hc and move some stuff around. You can say, you can have mv squared up top, 2 over hc equals 1 over lambda prime. So this is actually 2 steps of algebra. I divide everything by hc, and I moved this term to the other side. And then I can inverse everything to arrive at this expression. So we can plug in some numbers to get our lambda prime using the constants and everything else. I get a lambda prime of about 1.42 times 10 to the negative 10 meters. Now that we have this lambda prime, we can now get look at the Compton scattering equation. We can say lambda prime minus lambda, which is the change in lambda, is equal to h over mc 1 minus cosine theta. And we just need to find theta at this point. So we can do a little bit of algebra. We can start by moving the h over mc to the other side by dividing it through. And then in 2 more steps, we would end up with theta equals inverse cosine of the previous quantities, 1 minus mc over h, change in lambdas. So numerically, and I'll actually show the steps for this one, what numbers were actually used. H over mc is about 2.427 e to the negative 12. I have that saved because it appears so frequently. But we can substitute in the mass of the electron, as the speed of light, all over a Planck's constant. And then we take the difference in our wavelengths, 1.42 e to the negative 10, which is what we solved for earlier, meters. And then what's given, the 1.385 e to the negative 10. Oh, one more big parenthesis. And plugging all of this into our calculator, we will end up with this much simplified expression in the argument for inverse cosine. So negative 0.442. And finally, we are left with 116 degrees. So our scattered photon was deflected a little bit over 90 degrees with its new lambda. And our electron was scattered some way. So that's it. We were asked to find theta. We found theta using conservation of energy and the Compton scattering equation. Thank you very much.